Okay, all set.
Yeah, thank you. Hi, good afternoon. Welcome, everybody. It's a pleasure to welcome our distinguished speaker today, Raymond Yeung, who is Chou-Ming Lee Professor of Information Engineering at the Chinese University of Hong Kong. And he's also co-director of the Institute of Network Coding there. Raymond got his undergraduate degree and his graduate degrees all in Cornell, and then he joined AT&T Bell Labs. After doing that, in 1991, he joined the Chinese University of Hong Kong, and he's been there since. In 1991, he joined CUHK. Now, as we all know, he's made pioneering contributions in several directions. So in some sort of chronological order, starting with information inequalities, and then with Zhenjiang, he discovered the first unconstrained non-channel type inequality. And this has always been a little forbidding for me because it means or implies that if there are problems in multi-user information theory whose answers are in terms of these non-channel type inequalities, then it's going to be very tough to write converse proofs. So
yes.
And then he also has worked on machine proving of such inequalities. And of course, his standout contribution has been his celebrated network coding and its applications. He taught the first MOOC on information theory, and today there are 60,000 students who viewed it.
I suspect that many of them are repeating.
Yeah. And then he's written a number of books, first on information theory, and then the revised version was a book on information theory and network coding. He has a monograph with Shenghao Yeung on batch code. These are batch sparse codes. And then, of course, his work has been recognized by a long list of awards. I'll just mention three of them. First, the Information Theory Society Paper Award, and then the 2021 Richard Hamming Medal, and the 2022 Claudine Shannon Award. Now, I could go on and on, but of course, I don't want to stand between you and your talk and the rest of us. I'll just mention, and I'll mention that on a personal note, Raymond and I go back a very long way, and we have shared interests both in information theory and in photography, and we have this running exchange going on a regular basis. And with that, Raymond, it's all yours.
Thank you very much, Prakash, for the very kind introduction. I almost couldn't recognize myself. Okay, so today I'm going to give a talk with a very simple title, Inequalities Revisited. I can assure you that this is one of the simplest talks that you have ever been to. And actually quite surprising, this is a follow-up work on some of the works that I did in the late 1990s, which is almost like 30 years ago. Okay, so here's the outline of the talk. How can I make this smaller on the screen? This is blocking my way.
Just press OK.
Yeah, it is good and shit. Yeah.
I couldn't. Oh wait, I couldn't find the cursor. Okay.
Yeah.
Like this. Oh no, not here. Here. Okay, I think that would do it. Okay, so as I mentioned, this is a follow-up work on my own work almost 30 years ago, which was on the study of entropy inequalities, which had led to very fruitful results in related fields. And so about a year and a half ago, I just realized that this geometrical framework therein can be applied to any general inequality, which I'm going to talk about. And so in this talk, I first will talk about inequalities and universally quantified inequalities. The latter means that under certain conditions an inequality holds. And and then I'll talk about the background of this work, which is on the study of entropy inequalities in information theory. And then I'll apply the same framework to three very well-known inequalities. One of them is the AMGM inequality, and the second one is the Markov inequality in probability theory, and the third one is the Cauchy-Schwarz inequality. And you're going to see what is going to happen when this framework is applied to these well-known inequalities. Okay, so first the first part of the talk is on the background. So this is about geometrical interpretations on inequalities. Okay, so we consider the Euclidean space Rn and a function fx, where x is a vector in Rn. And the inequality fx greater than or equal to 0 can be identified with a certain region in Rn, like this, okay, x in Rn such that fx is greater than or equal to 0. For an inequality, you can identify it with a region. And so if you set the inequality to equality, this becomes the boundary of the region if f is quote unquote continuous. I won't get into the details, but intuitively this is the case. So it will look something like this. This is fx is equal to 0. I'm sorry, I cannot use the cursor for some reason. So fx equals to 0 is the boundary of the region. Fx greater than or fx strictly greater than 0 is the inside of the region, and the fx less than 0 is the outside of the region. It's outside of the region. Okay, so this is something like this. So this is how we think of an inequality geometrically. Okay, so what is universally quantified inequalities? Let me give you just some examples. Actually, we are all very familiar with this. For example, the inequality for all x in R such that x squared minus 2x plus 3 is greater than or equal to 0. Okay. And the AM-GM inequality, which says that for any finite set of non-negative real numbers, the AM is always greater than or equal to the GM. Okay. And then the Markov inequality in probability theory says that for any non-negative random variables t, and for any positive number a, we have the probability that t greater than or equal to a is less than the mean of t divided by a. Okay, very simple. And the Cauchy-Schwarz inequality says that let V be a real inner product space. Well, I'll stick with the real inner product space for the discussion in this talk. That's sufficient to illustrate the point. For any for all vectors u, v, and in capital V, we have the inner product, the square of the inner product of u and v is upper bounded by the inner product of u and u and multiplied by the inner product of v and v. Okay, and in probability theory, we have the independence bound for entropy, which says that, the simplest case, says that for any discrete random variables x1, x2, we have entropy of x1 plus entropy of x2 is lower bounded by the joint entropy of x1, x2. Okay, so these are all universally quantified inequalities. In fact, virtually any inequality that bears a name is a universally quantified inequality. So the question I ask is there a geometrical interpretation of such inequalities? Okay. Means that under certain condition, the inequality holds. Yeah, basically it's just that. I actually didn't know this term, but I looked it up from mathematical logic, and this is how they universal means that under certain condition, something always holds. Yeah.
Certain qualities is classic.
Yes, but this is how they describe such inequalities. Yeah. Anyway, yeah. So let us go back a little bit in history, which is regarding the study of entropy inequalities in information theory. Okay, so for the benefit of this audience, let me just define the Shannon entropy for a discrete random variable x. It is defined as minus summation x px times log px, where the base of the logarithm can be taken to be any convenient positive real number. And for two random variables x and y, the joint entropy is defined like this. Entropy of x comma y is minus summation over all xy in the support px log pxy times log pxy. Okay, so you can define this for any finite number of random variables in the same fashion. Now I'm going to introduce a notion called entropy vectors. So we fix the number of random variables to be n, and for any n tuple of random variables x1, x2 up to xn, there are 2 to the power n minus 1 joint entropies. For example, for n equals 3, there are 2 to the power 3 minus 1 equals 7 joint entropies, namely the entropy of the single variables, the entropy of the pairs, and the entropy of the triple. Okay, there's 7 of them. Now, for every joint distribution for these n random variables, we can compute the 2 to the power n minus 1 joint entropies. Okay, so it becomes a what I call an entropy vector. Okay, so and this corresponds to a vector in R to the power 2n minus 1. You think of it in the Euclidean space, and then you plot a point over there. Okay, so here I'm going to introduce a very important region called gamma n star. Okay, so as I said, you have any joint distribution on n random variables, you can obtain a 2 to the power n minus 1 dimensional vector. And now I'm going to use this as an illustration, okay? So this is a 2 to the power n minus 1 dimensional space with the axis being labeled by the subsets of the indices, okay? So this is, it's being covered up, it should be H alpha and H beta over there. Okay, so as I said, you have joint distribution, you have a vector, you plot a point in the Euclidean space. And then by exhausting all possible joint distribution for n random variables, you can keep plotting the points, okay, like this, exhaust all the points, okay? And then the union of all these points forms a region, which is specified by H in R to the power 2n minus 1, such that H is an entropy vector, which means that it corresponds to entropy vector of some joint distribution. Okay, so you keep plotting all the points and form the space. And we call this this subset of R to the power 2n minus 1 gamma n star, where n corresponds to the number of random variables. Okay. Now, it turns out that if you take the closure of gamma n star, in general, it is not even closed. Okay. If you take a closure of this region gamma n star, it is a convex cone. That's why I draw it this way. Now, it turns out that this region gamma n star is very, very important because it characterizes all entropy inequalities involving n random variables.
The positive cone, right?
I'm sorry?
Positive.
Is it positive? It's a positive. Yeah. Yes, in the positive quadrant, yes. Okay, so let's take a look at this situation. We have an inequality which is a linear combination of the joint entropies B transpose H greater than or equal to 0. And let's say this inequality always holds. So let's take a look at what it means geometrically. Okay, this is the region gamma n star. And this is a half space induced by B transpose H greater than or equal to 0. Okay. Here's the situation that the half space completely contains gamma n star. So whatever joint distribution you come up with, you calculate the entropy vector is going to be in the region gamma n star. Because gamma n star is completely contained in this half space, it always satisfies the inequality B transpose H greater than or equal to 0. Okay, so this is why this region is very important. In the other situation, you would have something like this. Okay, so the half space does not totally contain gamma n star. In this case, it's possible to come up with a joint distribution with the entropy vector lying on the wrong side of the inequality. Okay, in this case, the inequality does not always hold. So this is a geometrical interpretation of what it means by the inequality always holds. So once you know gamma n star, you know exactly which inequality holds and which inequality does not always hold. Okay, so now next I'm going to introduce a related region called gamma n. Okay, so we use x alpha to denote xi and alpha, where alpha is the index set. It's well known that for any n random variables x1, x2 up to xn, they satisfy the so-called polynomial axioms, which consists of 3 inequalities. The first one is non-negativity. Okay, entropy of any collection of random variables is non-negative. Non-decreasing means that entropy of X alpha is less than or equal to entropy of X beta if alpha is a subset of beta. Okay. The third one is so-called a submodular inequality, which says that for any alpha and beta which can overlap, okay, entropy of X alpha plus entropy of X beta is lower bounded by entropy of alpha union beta plus entropy of alpha intersect beta. Okay, so each inequality corresponds to a half space in the Euclidean space, right? Okay, and so we let gamma n be the intersection of all these inequalities, so it becomes a polyhedral cone. Okay, so because these inequalities are always satisfied by any joint distribution, by the discussion in the last few slides, okay, like this, okay, we immediately see that get all this. Right here, okay. We immediately see that gamma n star is contained in gamma n, because gamma n is just the outer bound of gamma n star. Okay, so next I'm going to talk about Shannon type inequalities. Okay, if gamma n, which is the polyhedral cone formed by these and let me see, I think I missed something here. Oh, okay. Well, so these so-called polymetroidal axioms, but it turns out that this set of inequalities is actually equivalent to the non-negativities of all Shannon's information measures, like entropy, conditional entropy, mutual information, and also conditional mutual information. They are the equivalent to this set of inequalities. Okay, so if it turns out that gamma n, which is the polyhedral cone defined by these polymetroidal inequalities, is a subset of the half space of a certain inequality B transpose H greater than or equal to 0, like this. So gamma n star is this one, and gamma n is an outer bound of it. Okay, and if it turns out that the half space B transpose dot H is greater than or equal to 0 completely contains gamma n, then we call this a B transpose H greater than or equal to 0. We call this a Shannon type inequality. Okay, because the Shannon type inequality is implied by the polymetroidal axioms, which corresponds to the non-negativities of non-negativity of all Shannon's information measures. Okay, so if it is a Shannon type inequality, then whatever joint distribution that you come up with, it has to lie in gamma n star, which in turn lies in gamma n, which in turn lies in this half space B transpose H greater than or equal to 0. So a Shannon type inequality is one which always holds.
The B is fixed? Or
B is fixed there.
and it doesn't make a difference if you shift it around?
Well, I mean
If you choose another B. Then
if you have to choose another B, then the inequality may or may not always hold. Yeah.
okay.
Yeah. But for any fixed B, we want to know
Yes.
whether it always holds or not. Yeah. Okay, so now it turns out that now if you look at this picture, once you formulate the problem this way, it's not apparent that gamma n is equal to gamma n star. Okay, so without this formulation, it's actually it's a bit abstract to think about, whether the Shannon type inequalities are tight or are complete or not. But once you put it in this framework, it's very natural to ask this question whether the two regions are coincide or not. Okay, but it turns out that these two regions are not the same. In 1998, actually, there was some preceding work by Zheng and myself in 1997, in which of which we discovered that if you take the closure of gamma n star, there are certain region on the surface which is not on the boundary, which is not achievable. Okay, but turns out that the gap is bigger than that. Okay, so it turns out that there exist non-Shannon type inequalities for 4 random variables, not for 3 random variables. This inequality is very often called 0.98 or the Yeung inequality. people refer to this as the Zhang-Yang inequality, but there was another one which was discovered earlier called Z197. Okay, so the situation is like this. This is gamma 4 star, the 4 random variables, and this is gamma 4, and this non-Shannon type inequalities actually cuts through the gap between the two regions. And I owe Zhenjiang a lot for this discovery of this inequality. And what happened was that in this improving this inequality, he used a very strange technique, okay, which is nowadays called a copy lemma, okay, which I won't get into the details. And after more than 20 years, okay, we still don't understand why this technique works. And that's still essentially the only technique that can prove a non-Shannon type inequality. Okay, so it's very mysterious. And so with this, it shows that gamma 4 star, even if you take the closure, is not equal to gamma 4, which is the region characterized by the non-negativity of. I'm sorry. Yeah. For this particular inequality, but not for gamma 4 star. Gamma 4 star is. Yeah. It's a linear inequality. Yeah. Okay. And subsequently, other non-Shannon type inequalities were discovered. First by Doherty, Farding, and Ziegler. They actually use this formulation together with ITIP, which is a computational tool that for information inequalities that I developed with my student back in the mid-1990s. And they put it on a supercomputer and do a search, okay? And they were able to find, and together with Zhenjiang's copy lemma, okay? Without Zhenjiang's copy lemma, even a supercomputer cannot work. And Ken Ziegler told me that it took the supercomputer like on average a week to discover a new a non-Shannon type inequality. And Zhenjiang took a year and a half to find the first non-Shannon type inequality using his brain. Right? That's how I calibrate his computing power. It's really amazing. And without the copying lemma, even the supercomputer cannot find one. It's really that amazing. Okay, and then in 2007, Matouche found a class of non-Shannon type inequalities for 4 random variables. And it's really remarkable because not only that he proved that analytically, but he also proved that there's a curvature on the closure of gamma 4 star. Okay, so even gamma 4 star bar is very difficult to characterize. Okay. And Terence Tao actually has a very interesting blog on this subject entitled Special Classes of Shannon Entropy, which you can look up on the internet. Okay, now, yes.
Between the gap between the gamma 4 and gamma 4 star, I mean the boundary gap, is there a way to find a bound about like because the gamma 4 has a boundary, right? And gamma 4 star has a boundary. So we know there exists a line which between these two boundaries. Or do we know the gap between the two boundaries? Like
Actually, there's no exact characterization for gamma 4 star bar. At this point, it's already very tough. Even if you take the closure, it's already very difficult to characterize. One of my former PhD students, is courageous enough to look into gamma 4 star itself. Look at the boundaries of gamma 4 and characterize what can be achieved and what cannot be achieved. It's an extremely tough problem. Yeah.
Is the inequality developed? I guess that's the question. Is ZY98 outside the closure of gamma star, gamma 4 star?
Does it touch the point that touch the okay. A certain part of that inequality is achievable, but it's not tight. It's not tight. That's what I can tell you.
It's a point, right? So it's either the closure or it isn't.
I'm sorry.
It is a point. Either it's in the closure or it isn't.
Well, it is an outer bound. It's still an outer bound of gamma 4 star. It is an outer bound of gamma 4 star. That's all we know, and we know that it's not tight. Yeah. Okay, it turns out that this region gamma star is intimately related with many subjects in information sciences, mathematics, and even in physics. Now, on the right-hand side are four subjects: network coding, homograph complexity, a certain combinatorial problem, and finite group theory. And here I use a double arrow to mean that there's actually a one-to-one correspondence between gamma star and each of these subjects. Okay. On the left-hand side are five subjects: probability theory, quantum mechanics, cryptography, matrix theory, and matroid theory. And this single direction arrow means that there's implication of the studies of gamma star on these subjects, which in the interest of time, I'm not going to go through all of them, but I'll give you a taste of what's the connections could be. Okay, for a survey on this, I would refer you to a tutorial paper that I wrote in 2015. Okay, first of all, homograph complexity. Now, it was shown in a paper in 2000 by Hammer, Ramachenko, Shen, and Vereshchagin. These are mathematicians from the homograph schools, okay? And they showed that there's a one-to-one correspondence between entropy inequalities and homograph complexity inequalities. As an example, we know this inequality for Shannon entropy of x1 plus entropy of x2 is greater than or equal to entropy of x1 and x2. And the corresponding inequality for homograph complexity can be obtained by just replacing h by k. K stands for homograph complexity. Random variable x1 replaced by the string x1, and so on and so forth. And then you get a valid inequality for homograph complexity, and vice versa. Okay. For any inequality in the homograph complexity space, you can obtain a corresponding inequality in the entropy space, and vice versa. Okay. So now we know that there exist non-Shannon type, entropy inequalities. With this correspondence, you can also obtain non-Shannon type homograph complexity inequalities accordingly. Now, the sixth topic is group theory, which is also very interesting. This was discovered by my former student Terence Chen and myself in 1999. Okay, we let G be a finite group and G1, G2 up to Gn be subgroups. And we use the notation G alpha to denote the intersection of Gi in alpha.
These are non-abelian groups, right?
General finite groups, yeah.
Yeah.
Yes. And turns out that the intersection is also a subgroup. Okay, it turns out that there's a one-to-one correspondence between entropy inequalities and group inequalities in the following way. As an example, again, we have this familiar inequalities in entropy. So to obtain the inequality at the bottom, what you do is that you replace h by a log, okay, and then you have a fraction. Upstairs, you always have the order of G, which is the number of elements in the finite group. And downstairs, you have x1, the random variable x1, and you write the order of G1. Okay. The same thing for entropy of x2. You have a log of order of G over the order of G2. Okay. On the right-hand side, we have a comma, we have joint entropy, and what it corresponds to is that the H corresponds to log, and for the fraction upstairs, you always have the order of G, and downstairs, you have x1 comma x2, and here it corresponds to the order of G1 intersect G2. Okay, so you can obtain if that inequality on the top is valid, the inequality at the bottom is also valid. Okay? If you solve any entropy inequality, you can obtain an inequality for a finite group like this, and then it's also a one-to-one correspondence. You can also go the other direction. Okay, so as I mentioned, we have non-Shannon type entropy inequalities. So with this transformation, you can also obtain quote-unquote non-Shannon type group inequalities.
I have a question. The first one at the top.
Yeah.
That says that the mutual information is always positive.
Right.
Right. Now we can write this as a divergence.
Yeah.
So these these inequalities can be written, I think we've discussed it, that the divergence is non-negative. Can the conclusion that the correspondence not be drawn directly from there, or do you have to go through the entropy formulation? Because you
let
take
me
two
see.
joint distributions, then look at their marginals, they're independent, and look at the divergence, which is non-negative.
Okay, okay, put it this way. Okay, I can say that's the by far this correspondence cannot be. Let me see. Maybe I'll go on.
Okay, sure.
Next time I answer questions.
Sure.
Okay, so as I said, non-Shannon type group inequalities can be obtained. So for example, ZY98 would become something like this. Okay, where let's see, I can move this down. Okay. Okay, so it becomes like this. Okay, so so this is the finite group version of ZY98, and no one seems to be able to understand what it means. Okay, and so far no group theoretic proofs of such inequality exist. Okay, well, we've been trying a little bit, and because the strange thing is that this inequality, although it's a purely group theoretic, we don't know how to prove it directly. We have to go through entropy in order to be able to do it. Okay.
And what does the entropy form look like?
Entropy form. Actually, I didn't put it down here, but okay. So I think if someone can find a group theoretic proof of such inequalities, that can actually help to get the interest of the group theory community. Yes.
So you mentioned that there's this correspondence between the entropic inequalities and the group theoretic inequalities.
Right.
Is there a correspondence of the proof technique as well? So like something like the
yeah, I mean I know what you mean, but it seems to be difficult. That's why I encourage you to see whether you can find a group theoretic proof for such inequality. Yeah. Okay, so whether you can go you can skip entropy, I don't know. Okay, matrix theory. Specifically, I'm talking about positive definite matrices. Okay, so we let small h denote the differential entropy of a collection of continuously random variables. Now, by substituting the differential entropies of a Gaussian vector with covariance matrix K, where the covariance matrix K can be just any positive definite matrix. So any positive definite matrix specifies a Gaussian vector. For example, this independence bound for differential entropy, you just plug in the Gaussian form in terms of the covariance matrix K, then you can obtain the Hadamard inequality. Okay, like this. Oh, I think I need to get rid of myself again. Okay.
How about you press on that little one, the one on the left?
Then I don't see myself. I only see Darcy. Yeah, Darcy is want to keep me in the picture there. Anyway. Okay, this technique actually is not new. I mean, as far as I know, it dates back at least to Bellman. Okay. So so likewise, non-Shannon type inequalities for positive definite matrices can be obtained. For example, from ZY98, you can obtain this. Okay, this is annoying. Okay, so it looks like this, where K alpha denotes a principal minor of a 4x4 positive definite matrix. Okay, so you obtain something like this, which is along the line of Hadamard's inequality, but it's much more complicated. And this holds for any positive definite matrix. And again, I don't think anyone really understand what it means. Now for 3x3 positive definite matrices, it turns out that there exists no inequalities on the principal minors beyond the polymetroidal axioms. And this is joint work with Terence Chen and Dongling Guo more than 10 years ago. But 4x4, there are already some new ones. Okay, yeah, I think I skipped the matrix theory. So I'm sorry.
Can't show that one directly.
This one is difficult. Okay, if you, I encourage you to try to do it directly.
So again, the same question, like, do we understand the copy lemma in this context or?
We didn't look at this specifically. I encourage you to look at it. Okay, so I'm going to talk about applications of this geometrical framework that we use to study entropy inequalities to inequalities in other fields, which are non-entropy related. Oh, okay. I think I want to go back to the slide. Okay, here on the left-hand side, we have probability theory, quantum mechanics, cryptography, matrix theory, and matrix theory. I would like to make a remark on quantum mechanics. Okay, so so we published this paper on CY98 in 1998. Okay, and then I received an email from a person called Nick Pippinger. Okay, it turns out that Nick Pippinger looked at this problem very closely in the early 1980s. He didn't get anywhere, and he published it as an open problem. He gave it out an open problem in the conference in 1986. Okay, so after the publication of this non-Shannon type inequality, he got interested in this again, and he looked at the von Neumann entropy. Okay, and I think he had a paper in 2003 proving that for von Neumann entropy, there's nothing beyond the so-called strong subadditivity inequality for von Neumann entropy. Okay, and then this work actually inspired some other work by Andres Winter and also Lyndon Winter. And I think in some years later, they were able to prove that for four systems in quantum mechanics, there exists something beyond the strong subadditivity property for the von Neumann entropy, okay, which I'm not very familiar with, but this is something I would like to remark on. Okay, about a year and a half ago, I all of a sudden realized that this geometrical framework can also be applied to other inequalities. I was wondering why I didn't realize that for the past 30 years. Okay? And so let's take a look at a very simple inequality in algebra, the AMGM inequality. So we consider a finite set of non-negative numbers, x1 up to xn. And this is AM is the AM, GM is GM. Everybody knows that. And we know that AM is greater than or equal to GM. Okay. Now here's the line of thought again. Here the two quantities of interest are AM and GM, which I color coded in red and blue for easy recognition. Okay, and these are two quantities of interest, and we're interested in their relation. Okay, and the AM-GM inequality is a characterization of this relation. Okay. Now the question here is should I get rid of myself?
You could get rid of that insert for the time being and bring it back at the end of the talk. Yeah. It won't disturb you.
Yeah. I'll get rid of myself. Okay. Okay. Now the question I ask is, does there exist other constraints on AM and GM? All right. Okay, so here's a geometrical way to understand the GM inequality. So we let A and G be real numbers such that, A is in red and G is in blue, okay? The tuple, the pair AG is equal to the AM and GM respectively for some finite set of non-negative numbers, okay? And according to the AM-GM inequality, we have A always greater than or equal to G, right? And since xi's are non-negative, we also have the AM always greater than or equal to 0 and GM always greater than or equal to 0. Okay, so now we have three inequalities: A greater than or equal to G, A greater than or equal to 0, and G greater than or equal to 0. However, the inequality A greater than or equal to G and G greater than or equal to 0, okay, implies A greater than or equal to 0. So actually this inequality A greater than or equal to 0 is redundant. So we only have two inequalities, right? So we only have this and this. Okay. Okay. So now I'm going to define a region epsilon. Okay. Now the same old trick, right? Regard A and G as the coordinates of R2. And we let this region be all the AG in R2 such that G is greater than or equal to 0 and A is greater than or equal to G. Okay. So it looks like this. This the AG plane, and this inequality is this A equals G, and it go up as A greater than or equal to G, and this is G greater than or equal to 0. Okay. Okay, here's a very simple proposition. It says that for any AG in this region, there exists real numbers, non-negative real numbers xy, such that A is equal to the arithmetic mean of x and y, and G is equal to the geometric mean of x and y. Okay, it's very simple propositions, and the namely that A and G are the AM and GM of the set xy, respectively. And the proof is very simple. You just let x is equal to this and y is equal to this. Okay, and just to note that the A from A greater than or equal to G and G greater than or equal to 0, that we know that x and y are both non-negative. Okay, that's a very simple algebra. Okay. So the implication is that is the following. Okay, now if AG is equal to the AM and GM of some finite set of non-negative numbers, when we call AG an achievable pair. Okay, what the previous proposition says is that all the points in the region is achievable by some pairs, by some pairs xy. Okay, and so because of this, we also have the same interpretation as we have for the entropy inequalities. So if for any f function fag greater than if the inequality fag is satisfied by all achievable pairs, then we have the epsilon is a subset of this region defined by the inequality. Okay, the same thing as for entropy inequalities. So what could this function fag greater than this inequality fag greater than or equal to 0 means? Okay, if fag is equal to A minus G, then fag greater than or equal to 0 becomes A greater than or equal to G, which is the AM-GM inequality, right? So because of the proposition I just mentioned, this region actually completely characterizes all constraints on the AM and GM of any finite set of non-negative numbers. There's nothing more, okay? And so in other words, if another way to put it is that if an inequality fag is greater than or equal to 0 is satisfied by all achievable pairs, then it must be implied by G greater than or equal to 0 and A greater than or equal to G, because the inequality because the region corresponding to the inequality completely contains the region epsilon. The region epsilon is defined by these two inequalities. Okay. So there's no more inequalities regarding AM and GM other than put on F and no condition. No condition. No condition. Not no, the continuity it was just a way I just assume some kind of continuity to draw you that picture, but you don't need that picture. Yeah. At the beginning, I just assume continuity so that I can say that Fx equals 0 is the boundary of the region. There is nothing more than that. You don't.
Then what kind of set is Y?
What kind of set is Y?
Y set is what kind of set?
It is the set of okay. This is the set. Okay.
Not there, but then general.
In general, I mean, in the context of AMGM, this is it means in this context, all the points here are achievable, and all the achievable points are here. This is this corresponds to the gamma star in the context of entropy inequality.
Can any 2 points be arbitrarily close to each other?
Which is arbitrarily close to each other?
Can I have 2A and A prime, G and G prime?
Uh,
Can they be as close as possible to each other and still be there?
I'm not sure
What kind of set is Y? Is it countable, non-countable?
Oh, this is a very simple set. This is a
Density.
this set is just this. It's this very simple.
Yeah, but then we cannot see anything else about A and G. It's there's no gaps, no irrational, right? I don't know.
Yeah, well, we can discuss this offline. Yeah, if you don't mind.
A large to G, right?
I'm sorry.
This is A large to G, and your next figure is
A is larger than or equal to G. Oh, maybe yeah, it should be. Yeah, it should be G and A. Yeah, yeah. Thank you. Yeah, I drew the picture in the wrong way. Yeah, thank you. Okay, so this is the picture. Okay, so if an inequality FAG greater than or equal to 0 holds for all AMGM pair, that this region must totally contain the region epsilon. Okay. And on the other hand, if it doesn't totally contain the region, then you can always find a point which is lying on the wrong side of the inequality. Right. So there's nothing surprising at all for the AMGM inequality. Basically, it completely characterizes the relation between AM and GM. Okay, let's take a close look at the Markov inequality. Okay, so this is the Markov inequality, as I mentioned. Again, I use the color code red and blue. Okay, and or we can write this as expectation of t greater than or equal to A times the probability that t is greater than or equal to A, because A is strictly positive. Okay, so again, the expectation of we have a random non-negative random variable t and expectation of t, and also the probability that t is greater than or equal to A are two quantities we are interested in. Okay, and we're in particular we are interested in the relation between them, and the Markov inequality is such a relation, okay, between these two quantities of interest. Okay, so for the rest of the discussion, let A be fixed. And so this is the Markov inequality. Again, we let P and M be coordinates of R2. P is the red one, which corresponds to the probability. M is the blue one, which corresponds to the mean. Okay? And we define the achievable region to be psi A star, okay, which is the set of all pairs PM, such that PM P comma M is equal to P is equal to probability of t greater than or equal to A, and M is equal to the mean of t for some non-negative random variable t. Okay, and since P is a probability, it lies between 0 and 1, we can define the outer bound induced by Markov inequality as such. Okay, so this is psi of, so this psi A star, which is this the achievable region, and this is the outer bound induced by the Markov inequality. So m greater than or equal to AP corresponds to there, expectation of T greater than or equal to A times probability of T greater than or equal to A, and we also have an additional inequality for P between 0 and 1. Okay, so we know that because the Markov inequality is satisfied by all non-negative random variables, we know that psi A is the outer bound of psi A star. Okay, the question is whether these two regions coincide. Okay, so here it is. So this is the region psi A, which is the outer bound, and we want to see whether every point in this region is achievable by some non-negative random variable T. Okay, it turns out that it's almost the case. Now, if it is not the case, then there would exist constraints on P and M beyond the Markov inequality. Okay. Turns out that it's almost the case, except that this part is not achievable. This part on the m-axis is not achievable for a very simple reason. So the okay, let's take a look at okay, let's see. Okay, now the let's see. Okay, the reason is very simple, as I mentioned, because when the P is exactly equal to 0, which means that the probability that P greater than or equal to A is equal to 0, okay, it cannot achieve any value beyond A, then the expectation must be at least at most equal to A. It cannot be larger than or equal to A. Once you set P equals 0, which is you set this probability to 0, then the expectation must be strictly less than A. Okay, it's just as simple as that. Okay, nothing surprising. Okay. Any other point you can find a non-negative random variable to achieve. Yeah, you will be able to construct every point here, but not beyond this. Yeah, yeah. So no surprise. Okay, otherwise there could be another inequality which is
Either way, it's not close.
it's not close, right? Exactly. Okay, let's now take a look at the Cauchy-Schwarz inequality. Okay, so we let V be a real inner product space. As I mentioned, we only need to confine to real inner product space to to see the point. Okay, and for vectors UV, any UV, we have this the celebrated Cauchy-Schwarz inequality. Okay, here the three quantities of interest are these three. Okay, and again we are interested in the relations, and so we define the achievable region in R3 in exactly the same way as we did before. So this is the this is phi star. Okay, phi star is all the triples x, y, z such that x is equal to UU, y is equal to VV, and z is equal to UV for some vectors in the inner product space. Okay, and since the inner product of a vector with itself is always non-negative, okay, by the axiom of the inner product space, we can define the outer bound induced by the Cauchy-Schwarz inequality like this. Now this one, z squared is less than or equal to xy is just the Cauchy-Schwarz inequality, and we also have x and y are non-negative. Okay, and so again the question is whether phi star is equal to phi. Okay, we know that phi is the outer bound of phi star, and we want to see whether the two region coincides. Okay, this is what it looks like. So this is X, Y, Z, it looks like a bullet, okay, shooting into the origin at a 45-degree angle. Looks like this. And the this is Z squared equals XY, and Z squared less than or equal to X times Y fills out the inner part. Okay. Okay, so here's a very simple theorem. Okay, for an inner product space V, phi star is equal to phi if dimension of V is greater than at least equal to 2. If dimension V is equal to 0, then phi star is equal to 0. If dimension V is equal to 1, then phi star is equal to this corresponds to the Cauchy-Schwarz inequality, except that you set the inequality to an equality, okay, which is the boundary, okay, of that shape. Now, the proof of this theorem hinges on a proposition, which is very simple and intuitive, but I'm going to explain a little bit to you. So this proposition says that if dimension of V is at least equal to 2, then for any non-zero vector U in V, there exists a unit vector W such that U and V are orthogonal. Okay, intuitively correct, right? If the space is at least two-dimensional, then you have a vector like this, you can find an orthogonal vector to it. Okay, basically that's it. Okay. Now the proof is, however, I'd like to make a remark on the proof. The proof is you just work on the axioms of an inner product. However, I would like to remark that the proof of proposition 1 actually invokes every axiom of a real inner product space. Okay, namely that UV is equal to VU, and AU plus V comma W is equal to A times UW plus B times BW. UU is greater than 0 if U is not equal to 0. Okay, you have to use every single axiom. You cannot miss any one of them to prove this proposition 1. Okay. So the okay, so this is the theorem, and so here are the conclusion remarks actually. If dimension V is equal to 1, then phi star is the boundary of phi. Okay, where phi is this thing here. Okay, when the dimension is equal to 1, only the boundary of phi can be achieved. When the dimension is 0, only the origin can be achieved. Okay, that's obvious. Okay, so the Cauchy-Schwarz inequality does not completely characterize the relation between these two quantities when dimension V is equal to 0 and 1. Nevertheless, there exists no inequality on these three quantities that holds for all inner product space, regardless of the dimension of V, which is not implied by Cauchy-Schwarz. In some sense, Cauchy-Schwarz is quite complete here. Okay, so this brings me to, okay, again, for dimension equals 1, only the boundary can be achieved. Okay, here's the conclusion. So we propose a geometrical interpretation that captures the very meaning of a universally quantified inequality. Okay. Specifically, such inequality is an outer bound on the achievable region. There's some message to take home. Okay. So the ultimate problem is to completely characterize the achievable region. Okay. And we have applied this approach to the AMGM inequality, the Markov inequality, and the Cauchy-Schwarz inequality. And the results are not really surprising, but help clarify the issues. Okay. And well, as I mentioned, this geometrical framework had led to very fruitful results in a number of subjects related to the Shannon entropy and also to the von Neumann entropy. And in particular, non-Shannon type inequalities were discovered. Now, applications to other branches of mathematics may lead to the discovery of new fundamental inequalities on quantities of interest. Although for these three very simple inequalities, I look into there's really no new discovery. But potentially, if you apply this to your favorite inequalities, there's something new may come up. Okay? And for further details, I will refer you to a paper I've archived there. This brings me to the end of the talk. Thank you.
Thank you.
Oh, right on time.
Thank you. Next question.
What would be good candidates to look at beyond the three inequalities that you mentioned?
For example, some inequalities in coding theory, for example.
Will this apply to Raymond divergences? If I can I get the information according to this from Raymond divergences?
One thing is that since
Okay,
Prakash,
you don't-
you mentioned the KL divergence. Okay, well, it is
It's a very simple example. You can go to general.
but it's already complicated enough. Okay, I'll tell you why. Okay, now the okay, we talk about this region, gamma n, which is the on the non-activities of Shannon's information measures. Okay, it can be completely characterized as a polyhedral cone, and if you want to determine whether an inequality is a Shannon type inequality or not, you can formulate it as a linear program. Okay, however, it is already very hard to completely characterize what you can derive from the non-activities of the KL divergence. It's already very difficult to characterize. Yeah. Okay. With this formulation, you can completely characterize so-called Shannon type inequalities. The Shannon type inequalities are all we knew in the past. Okay? Now, before you can completely characterize what you already know, it's very hard to tell whether something you discover is new or not.
Well, I don't know. I'm interested about the comment you made about the KL.
Oh, the KL okay. What I'm saying is that it's very difficult to characterize everything that you can ever derive from the KL divergence, the non-activity of the KL divergence. It's already very difficult to characterize.
One step back, because the non-negativity of the KL divergence is a consequence, for instance, of the log sum inequality, which is more general.
It's more, yeah.
So
But if you ask me, I have this inequality, is it derivable from log sum inequality? It's very difficult to tell. Yeah, in fact, the key of obtaining the non-Shannon type inequality is that you first have to tell whether an inequality is of Shannon type or not. Okay. In fact, what happened was that during that time, Zheng Zhang was spearheading the problem. He came to me once in a while saying that I've discovered new inequality. I then run it through the ITIP, the linear program, and check whether it is old or new. Okay, if the linear program can prove it, oh, I'm sorry, go back. Okay, so
What happens if I use different entropy? Like if I use Remy entropy?
Differential entropy. Okay, now I
I
think it's already quite difficult to completely characterize. Yeah. I don't, not to my knowledge. Not to my knowledge.
And the other question I have with respect to phenomenography, are you referring to essentially quantum information theory or not?
The quantum. Yeah.
Because there are other inequalities. Right?
Yeah. Right. So people already discovered something new in that domain.
More.
Yeah.
So general question. So what do I care to prove? In weird inequality groups here. Because I'm not going to get that.
Good question.
They give a good theory, but they will not even touch the story.
Yeah, good question. I mean in fact, I had a conversation with Lieb like almost 20 years ago, and he said he couldn't understand what this inequality means. Yeah, it's but I mean they must mean something, except that we don't know what they mean.
The sum of inequality from a lot of complexity is not surprising at all.
Right.
Right, because they're very well connected.
Yeah.
So, but the others are
for non-Shannon type inequality, actually one okay, let me go back to this. I'm sorry. Because they're not derivable from the non-activities of Shannon's information measures. Because for a long time, all the inequalities that we invoke in improving information inequalities are actually the non-activities of Shannon information measures. Yeah. And in fact, for the general network coding problem, the complete characterization is in terms of gamma star. Yeah. So it does. There's certain problems in the general network coding problem that requires non-Shannon type inequalities to characterize. In fact, when we discovered this inequality, Zheng and I were very excited. We hoped that it could settle some open problems in information theory, but we couldn't find those problems. At the end, we found that one application is actually in network coding. But potentially, if the networks become more complicated, I think these non-Shannon type inequalities will kick in.
Yes, so that's why I have a fear that to prove converse results in those settings will become.
Oh, but you can incorporate those non-Shannon type inequalities into ITIP.
That's right. Questions? More questions? So back to my other questions I have. You look at the set, Y, gamma, whatever you call it. Okay? You know these properties of sets, whether by rational numbers, whether they're dense or not dense, and so on and so forth. What type of set it is? What is the density of the set?
Okay,
Because if I find 2 points A and A prime in all these two things, can I find the function of that or not?
Okay.
Not the boundaries, the set itself.
This, as I mentioned, this set is not closed. Okay, this set is coming star. However, it is solid inside. Okay? Inside the region, you cannot find a hollow space. Okay, so only
That's for all the sets.
that's what
It's for all the sets.
for all the sets for
You have
entropies.
this problem.
For entropies, yes.
So that means F has some properties. It cannot be just anything.
And yes, correct, right. And
so
so
you give you 0, 1 function, and you cannot give it.
yeah, right. And but the F can be very general. The F can be it
It
can
has to be continuous, I think.
yeah. The F can even be an indicator function, whatsoever. The F function. This let's see. I mean this F can be it can be any set, can be any indicator function.
That I don't believe, but anyway.
But you can define any way you want. I mean, you can. So this F actually can characterize any subset of R2, whatever you in any way you want. This claim still holds, and this claim still holds.
Okay.
Yeah.
Let's leave it at that. More questions? Well, thank you very much for a thought-provoking talk.
Okay, thank you very much. Well, I hope that this talk is is understandable, yeah, to everybody. I hope.
There were lots of questions.
Okay, thank you again.
Thank you.